All right, so we were in the last video and I was cut off. We were going to multiply all, 365.26 times 24 times 60 times 60, and the number you get is about let me write this down. So 536 times 10, that's a 0, 10 to the 7th seconds. All right, so that's really what you have to do to convert it, to convert years to seconds. So we know that in 1 year there are, you could just call it 3.15. That's perfectly fine. 3.15 times 10 to the 7th, 10 to the 7th seconds. All right, that's 10 to the 7th. All right, and so you just take this number one. So here's what it doesn't look very nice. V transverse, or you can call it tangential as well. Is going to be 1.5. 1.5. That looks a little better. Times 10 to the 9th kilometers in 3 divided by 3.15 times 10 to the 7th seconds. All right, and that'll get us in kilometers per second, which is the typical values that we use for astronomical velocities. And so this turns out to be 47.6. 40, is that right? Let's see, let me look at it again. Approximately 47.6 kilometers per second. All right, that's, and now we're not quite done. Remember, that's the transverse velocity. All right, so they also give us, so I'm going to let's write this down, okay? So we know the transverse velocity. So that's, if you look at it in terms of like a picture, it would look like this. This is the transverse velocity, and then the radial velocity would be directly towards us. All right, so we'll call that V sub r. And then V, the true velocity, is the sum of the two of these. So if you put one of these head to tail like this, and you start with where where the original object is, this is the actual movement of the object. Right? And so these two, the transverse and the radial, are at right angles to each other, or 90 degrees to each other. So this velocity right here is V. That's what we want to know. And so V, if it's a right triangle, it's very, very simple. Since that's the hypotenuse of a right triangle, V is the square root of V tangential, or V transverse squared plus V radial squared. All right, just because it's the it's the hypotenuse of a right triangle. All right, and so that's the true velocity. Right, that's the thing that they say, calculate the magnitude of its three-dimensional velocity relative to the sun. All right, so now we know what the transverse velocity is. We just worked that out. It was 47.6. All right, 47.6. That's a 7, and of course kilometers per second. And so we're going to want to know what this radial velocity is. But they give us information to find that. It says it is observed to be redshifted. So redshifted means, of course, it's moving away from us. So actually, I should have drew the arrow this way. But it's still the same right triangle. Anyhow, it's redshifted at 0.01%. So let's write that down. So it's redshifted by 0.01%. right? That's important that we recognize. So percent means, it means that, you know, I gotta put two more zeros, right? So it's gonna be 0.0001, right? So that's the shift, if you will, right? If remember when we did this little like delta lambda over lambda naught, that's equal to this, right? And remember what that is that's the velocity divided by the speed of light. In this case, so this right here is this fraction is that number, 0.0001, and so the velocity of this thing is going to equal, I'm just going to rearrange this equation, bring the speed of light on the other side. It's going to be 0.0001 times the speed of light. All right, just make that look like a times. And so in this case, we want to use the speed of light as 3 times 10 to the 5th. All right, so if I multiply, 0.0001 times 3 times 10 to the 5th, that's a 10 to the 5th, of course, kilometers per second. That's why we're doing it in kilometers per second. That becomes, 30, right? 30 kilometers per second. All right, so basically a redshift of 0.01% gives us a speed of 30 kilometers per second. So now we're going to use this equation right here, and we're going to use v sub r as 30 and v tangential as 47.6. All right, so let me get a new page here, and well, there we go. All right, so the velocity is going to equal, all right, remember, it's the square root of the transverse velocity, which was, what is it again, 47.6, so it's going to be 47.6, but we've got a square, it still has the units, I didn't put them, just I'm being lazy, plus the 30, right, that we just got from the radial velocity, and we square that. And so this is the true velocity, okay? So you take the square root of all that, you got to square each of those numbers, add them together, take the square root, and you get, so you should try this in your calculator, make sure you know how to do this. It would be 56.3, 56.3, and it's kilometers per second. Kilometers per second. All right, so that's the end of number 2. All right, so let's look at number 3. It says, what is the luminosity? Let me scroll this down a little bit. What is the luminosity of a star having 3 times the radius of the sun and a surface temperature of 10,000 Kelvin? All right, so how would we do that? So there's a relationship, it turns out. Let me look at the piece of paper here. There's a relationship between the luminosity, the size, and the temperature of stars, right? And so so it looks. This is number 3. Number 3. All right. So in number 3 again, let's see. It says we know. It says the star is 3 times the radius, right? So the radius of the star is equal to 3 times the radius of our sun. Now, I'm going to use that little symbol where, well, it's supposed to be a dot in the middle. Anyhow, and the temperature of this particular star is 10,000 Kelvin. Recall, the temperature of our sun, I'll just use the word sun, is 5,000, from chapter 16, 5,800 Kelvin, right? That's what makes it a G2 star. All right, so now how can we do this? How can we figure out let's see, what is it asking? What is the luminosity of a star? And so here we go. All right. And so the equation that you use is looks like this. It is the luminosity of a particular star is equal to, let's see, so it's going to be the radius squared, right? So it's going to be the radius squared times the temperature to the fourth. And the radius r has to be in solar radii. That's why it's 3 times the radius of the sun. And the temperature has to be, of course, the temperature is you were comparing the temperature to the temperature of the sun. So it's got to be in solar. Basically, you take this 10,000, you take whatever the temperature of the star is, divide it by the temperature of our sun, and that puts it in solar units. Okay, we'll do that right now. All right, so here we go. All right, so the luminosity is going to equal, so it's going to be 3. Remember, it's you square the radius, right? As long as it's in solar units, which it is, it's 3 times the, and then times the temperature. But it's got to be the temperature in solar units, so it's going to be 10,000 divided by 5,000. That's supposed to be a 5, 800. Right? But remember, we're raising that to the 4th power. Okay, so when you do this, numerically, it comes out to be, let's see, what does it come out to be? So it becomes 79. So the answer will be in, this is times the luminosity of the sun. All right, so this is some number times the luminosity of the sun. And some stars are more luminous than the sun, that number would be greater than 1. Some stars are less luminous than the sun, that number would be less than 1. All right, so this turns out to be 79.5. 79.5 times the luminosity of our sun. All right, so try that. 3 squared, and then take 10,000. You got to do this part first, the fraction, or what's in parentheses. So 10,000 divided by 5,800, and then take that and raise it to the 4th power. You multiply by 3 squared, which of course is 9, and you'll get close to 80. So it's basically about 80 times as bright, or 79.5 times as bright. So that was, what was that, number 3? That was number 3. This is number 3. All right. I did not mean to do that. All right. So that was number 3. And did I turn this thing off? All right. So number 4. We'll at least get this set up. I don't know if I'll be able to finish it. It says calculate the solar energy flux, which is the energy received per unit area, per unit time, as seen from a distance of 10 parsecs from the sun. Compare your answer with the solar constant. So I've actually set up what the solar constant, this is supposed to be meters. So the solar constant is the luminosity of the sun, which is 4 times 10 to the 26th watts, divided by the spherical shell, the surface area of a sphere with radius, the distance from the Earth to the sun. So it's 4 pi times r squared. So 4 pi times 1.5 times 10 to the 12th. Sorry, 10 to the 11th. But we got to square that, right? And that's in meters. So you got to do this one in meters. Remember, it's 1.5 times 10 to the 8th kilometers, but it has to be in meters to get these to get the watts to work out correctly. Anyhow, so this is called the solar constant, it's basically the flux that arrives at the top of the atmosphere, right? And so that turns out to be, it's a little more than 1,400. All right, so it's 14. I'll just write 1,400. So 1,400. Watts per square meter. All right, so watts is the amount of energy per unit time, so that takes care of that. All right, so that's, now, what if this R was increased to, what did they want it to be? 10 parsecs